Okay, today's lesson is going to be a fairly easy one. There's no new math to worry about, so that's always good news. Um, we've been assuming up until now that all gases are ideal gases, and they all obey the gas laws, Boyle's law, Charles' law, the whole PV equals nRT thing. Um, but recall what the assumptions were that we made to assume they were ideal. The first big assumption we made, you'll recall, is that the molecules have no size. They're infinitely small. That simplifies the math a whole lot. When we're calculating volumes, we don't have to worry about how much volume is taken up by each individual molecule. But of course, the reality is the molecules do have some size. They're just so small that to 3 significant digits, we usually can ignore it. The other simplifying assumption is that the gas molecules don't have any forces of interaction with each other. So when two molecules get near each other, we're assuming they just kind of zip right on by and don't attract or repel each other. Again, in the real world, that's a fairly valid assumption because they're going so fast in gases that they don't have much time to interact. But of course, in the real world, there are some forces. The electrons in one molecule might repel the electrons in another. The protons in one might attract the electrons in another. And so those intermolecular forces are there and they're real. We're ignoring them completely to simplify the math. For most gases, those two simplifying assumptions are no big deal, and the gas laws work very, very well. But at some point, and for some gases it happens more than others, you end up with situations where the molecules are big enough that it matters to the volume, that the intermolecular forces are enough that they matter to the amount of pressure that the gas is applying. So today let's look at real gases, gases as they really exist, compared to the ideal behavior that we've been assuming with our gas laws. Okay, so again, an ideal gas is one that follows the gas laws under all conditions. And just recapping, the particles have no volume. There's no intermolecular attraction forces between the molecules. Of course, in reality, that never happens. But again, it's close enough for 3 or 4 significant digits that we can go with it. Now, if you think about it, take Charles' law. As you cool down a gas, the volume decreases. At absolute zero, the volume would be zero. So a gas would shrink away to nothingness, and obviously that can't be true. That's because we're ignoring the fact that the molecules have size. And so we can let it shrink down to zero because there's no atoms to worry about. The other thing is, long before you reached absolute zero, the intermolecular forces would have made the molecules stick together, and the gas would have condensed out and become a liquid, and now the gas laws obviously wouldn't apply anymore. So in the real world, that kind of behavior happens, and so the gas will behave in an ideal manner until you get to maybe a low enough temperature where it starts deviating from the ideal, and Charles' law becomes an approximation. And you get colder yet, it becomes an even worse approximation, and eventually it just fails. Same with Boyle's law and all the others with pressure. As you increase the pressure, eventually the gas will become less and less ideal, and eventually Boyle's law just fails. Okay, and this is happening because the particles have real volume, they have real size, and they attract each other. So notice here they show an example. This guy doesn't look very happy, of a gas being condensed into a liquid. They don't say it, but it's probably liquid nitrogen because that's what they always use. Okay, so notice I mentioned this before, but real gases differ from ideal behavior generally when you get to low temperatures and when you get to high pressures. At high pressure, they're forced closer together and those intermolecular forces matter more. At low temperature, they begin to condense out and form liquids, and again, the size of the molecules and the intermolecular forces matter more. Now, how high is too high a pressure? How low is too low a temperature? Depends on the gas. A gas like hydrogen that has very, very weak forces and very, very small molecules will behave ideally way down close to absolute zero. Something like water vapor that has very, very strong intermolecular forces at room temperature is not ideal because it already is liquefied. In order for water vapor or steam to behave as an ideal gas, you need to be in the hundreds of degrees. So it varies from one gas to another. Notice again, for ideal gases, it doesn't matter what gas you're using. In those worksheets I gave you, I used the name of a gas in every single problem, and it meant absolutely nothing to you because you just plugged into the pressure, the volume, the whatever, and it didn't matter the name of the gas. That's because they were behaving as ideal gases. In the real world, it matters what gas you have because it will affect where the temperature is too low and where the pressure is too high for it to behave ideally. Luckily for us, in an introductory chem course, we don't worry about those non-ideal conditions. We just say, yeah, it happens, I can't do that. When you go on to AP chemistry, or of course eventually when you become chemistry majors, you're going to discover that there are equations out there like something called the van der Waals equation that take PV equals nRT and allow you to plug in mathematical correction factors and adjust for non-ideal behavior. But that's future U problem. This graph is kind of interesting if you're into graphs. Notice it's looking at how pressure deviates from ideal behavior. You could do a similar graph for how temperature deviates and so on. So along the x-axis, they're graphing pressure in kilopascals, notice. On the y-axis, they're graphing the ratio of PV over nRT. Now, ideal gas equation, PV equals nRT. So if gases were all ideal, PV divided by nRT, which it equals, should always equal 1. So notice at 1.0 here, a line going horizontally across, that's what an ideal gas would do. So if all gases were ideal, every one would have a graph that was just a horizontal line at 1. Look at hydrogen. Now, looks like it deviates pretty quickly, but look at the kilopascal scale here. 0, we're already at 20,000. Normal air pressure is 101, down here-ish, right? So at normal conditions, hydrogen acts like an ideal gas, and it all is well. When you got to get to really ridiculously high pressures before hydrogen behaves in a non-ideal behavior. But look at something like carbon dioxide, which has rather massive molecules, and the intermolecular forces are pretty decently strong because of something called polarizability. Notice it deviates very strongly from ideal behavior, even down here at fairly low pressures. The shape of the graph and why it curves back up, we'll leave that for future you to worry about. But the gas in that case deviates much more from ideal behavior. And so if you were working at, say, 20,000 kilopascals pressure, and you plugged the values PV into PV equals nRT for carbon dioxide, the results you get would be fairly far off from what they should have been, because you're assuming ideal gas up here, and in reality, it's way down there. If you work at very low pressures, CO2 might still be a bit of a problem. Something like hydrogen, or notice methane here with very, very weak intermolecular forces. Is that methane? I think so. Also would not deviate much from ideal. So whether how much pressure is too much that you can no longer use your ideal equations depends on which gas it is. Okay, and then finally is just the recap. Characteristics of an ideal gas. You know this already. No molecules, or no size to the molecules, and no intermolecular forces between them. Okay? I don't think this is anything important. Oh, by the way, I saw this earlier when I looked at it. That term they're using there is grammatically incorrect. I know it's chemistry, but they still should know this. They're writing textbooks. When something goes like dry ice from a solid directly to a gas, that's called sublimation. Sublime, well, in English class you'll learn what that means. But dry ice does not sublime, it sublimates. So I had to make fun of the textbook because I always do. That's it, and this is just now the rest of the PowerPoint you can look at is just a recap of the section. The main things here are PV equals nRT, that equation, we did that yesterday, and this idea of gases deviating from ideal behavior in the real world. So what I want you to do for today, and turn in by the end of today, whenever, is the section review worksheet. It's section 14.3, but again, remember the textbook is stupid, so they labeled it 12.3. I'll attach it right to this assignment so it's easy enough to find. Do that, upload it right here in the assignment, and then tomorrow we'll move on to the last section of the chapter. After we're done with that last section, we'll look at having a quiz on the second half of the chapter. I'm thinking now with the online stuff we're doing here, we'll break chapters up in half and do a quiz on each half, rather than having the big final cumulative test, which is terrifying anyway. But we'll worry more about that later. I doubt we'll finish the whole thing this week. Maybe, maybe not, but count on maybe having the quiz on that sometime fairly early next week. All right, that's all for today. Enjoy the worksheet, and I'll see you tomorrow.